Good morning, everyone. This will be the first of many videos that will be used to review and go over our exams and our quizzes this summer session. I thought it would be helpful to you to see these videos to help you study for next exams and also the final exam as well. And so, as far as quizzes go, one of your classmates had asked me if I could go over the quizzes as well, and I'm sorry I hadn't thought of that before, so I would have done it for the previous quizzes you had, the last two that you had last week. But for now on, after we're done with a quiz, so like when it's due by 8 o'clock the next day, I will post a video going over the quiz for you, so you know how you did or what you did wrong, so that way you can use the quiz videos to help you study for the next exam, and then use the quiz videos and the exam videos, review videos for studying for the final exam. Because if you're anything like me, you need all the help you can get when it comes to organic chemistry. So that being said, before I get started, excuse me, before I get started actually going over this exam, I just wanted to talk about a couple things. I know that a lot of you did not do as well as you were hoping to do. Just remember that you're taking organic chemistry in the summer. And if you recall from the very first lecture, I said that this was going to be difficult because we're covering a lot of material in a very short period of time. We're going to go very fast, and you're not going to have enough time to just absorb everything. So organic chemistry is already extremely difficult in class, in person, with a professor, and like tutors, and working in groups with your friends. It's already difficult. So having to do this class online only, and over the summer, such a short period of time. I mean, it really puts everybody at a real disadvantage, and it's definitely unfortunate. And so, I really need you to understand that for you to be able to be successful in this class, you need to not just know the material, like know the concepts, understand the concepts, right? But you also have to know how to apply those concepts. Organic chemistry is different from most topics, most subjects. Just to compare the three, physical / life sciences. In biology, I mean that's generally memorization, right? Vocabulary words and things like that. And in physics, I found that when I took physics as an undergrad, if I, knew the formula and memorized those formulas, and I knew which one to pick, I mean, it got me through physics. It was fine. But it's different with organic chemistry because organic chemistry is like a whole new language, right? You have rules and you have vocabulary that you have to know by heart, and then you have to be able to use those rules and that vocabulary and apply them to an infinite number of chemical reactions of molecules. I think the biggest mistake for students is memorizing, thinking that memorizing is all you need to do for organic chemistry, and that's absolutely not the case. You need to build a solid foundation, and that does require memorization, right, of the vocabulary in organic chemistry and the rules. And that way, when you see any molecule, it doesn't matter what molecule I throw at you, or the MCAT throws at you, or whatever, right? You'll be able to apply those rules and use your vocabulary to look at any molecule and decide what to do with that molecule, right? The goal here is to end up at a point where you can look at a big molecule or a small molecule, like a natural product, a drug molecule that is scarce. And the problem is that you have to be able to figure out how to build that molecule from scratch, just from the elements from the periodic table, right? And so that's really what organic chemistry is. It's a problem-solving class, but you're not going to be able to solve those problems until you build a very solid foundation in the rules and vocabulary of this language, so that you can become fluent in it, right? So to be able to do that, you've got to do practice problems. It's not just about listening to my lectures, and I know they're entertaining. I know you love listening to my lectures, right? I can see that from the YouTube views. But it's more than just listening to the lectures. You know, you have to go into the textbook and open up the textbook and look at the practice problems at the end of each chapter and practice those problems, right? You got to practice them over and over again, even ones that you've already done before. You've got to practice them over and over again, and soon, you know, it will click. It will click about how to do organic chemistry, how to speak the language fluently. I will tell you, for me, that it really didn't click for me until I got into grad school, because, and I'll be completely honest with you, when I was an undergrad, I actually failed Organic Chemistry 1 the first time around, okay? I had to take it a second time. But look at me now. Now I'm actually teaching it. You know, I have a PhD in chemistry and I'm teaching it. And that took a lot of hard work. And so, it's just that for some people it takes longer than others, and unfortunately, since you're taking this at a summer, you know, in a summer class, you don't have as much time for it to click, right? But when it clicks, man, organic chemistry is fun, because you see this molecule, and the question is, how do you build this molecule? And it's like, oh man, it's like building Legos, you know? And instead of Lego bricks being the construction materials for building, you know, a structure, it's the elements of the product table. It's absolutely the same thing. And so, yeah, I mean, organic chemistry was very difficult for me when I was an undergrad, and I didn't really get it until grad school, you know, and you know, I just want to end this by telling you just a couple of stories, okay? The first one, in general chemistry, actually, I took a class. I took my very first general chemistry class, and on the very first exam, I had this professor, and he actually ended up being my mentor, like, throughout my academic career. So, you know, thank you for helping me get through life. I'm gonna leave his name anonymous for now, but when I took his very first exam in general chemistry as a freshman, I actually failed that exam. I didn't just fail it, I got a 0 on it. And you may be asking yourself, how do you get a 0 on an exam, right? Well, he had this really weird grading system where he graded on a 5-point scale, right? It was like almost like a grade point average scale, like a GPA scale. And so 5 would be like 100, and a 0 would be anything below a 60. Right? So it was actually really easy to get a 0 on the exam. And so I ended up getting a 0 on the very first exam in general chemistry. And the next day we went back to class, and I was just so tired and so fed up, you know, with general chemistry, or chemistry just in general. And so he was going over the exam, and I had my notebook open, right, and it was on my desk, and I had my water bottle on top of my notebook. And of course I'm like falling asleep in class, so I have my hand on my face like this and my elbow on my notebook, and I'm just like kind of dozing off while he's you know, going over the exam. So I guess he noticed this, and he comes over to my desk, and he wakes me up by pulling my notebook, my open notebook, out from under me, which is blank, by the way. I'm not taking any notes at all because I'm just so tired of this. And so he pulls it out from under me, and he shows it to the whole class. Oh, I forgot to say, he actually took the time to move my water bottle to the desk next to me, right? And then pulled out the notebook out from under my arm and showed my notebook to the whole class. And he said, this is what he said. He said, and you know, I don't remember a lot of things from college, right? I mean, who does? But this one particular incident was quite memorable. He shows the class my notebook, and he says, if Fawn would take more notes in class, maybe he wouldn't gotten a 0 on the first exam. And wow, that was quite an experience there. And I took it, you know, I took it as a challenge. I said to myself when he did this, like, I can't believe this guy's like calling me out like this, all right? What the, talk about the shade, like call me out like this. So I spent the entire semester, you know, just hitting the books, practicing, and I ended up getting an A in the class because he dropped the first exam, right? He dropped, he dropped he dropped the lowest exam grade. So he dropped my 0, and I ended up getting an A in the class. And that experience in itself, right there, put me on the track to being a chemist, right? I had no idea I wanted to be a chemist. In fact, when I joined, or when I went to Sam Houston State University as an undergrad, I was a CJ major. So, I mean, I had no idea I wanted to be a chemist until that experience happened, okay? I also have one other story to tell you, and it's about another professor, okay? When he was an undergrad, he was taking organic chemistry, and let me just tell you, he's actually an organic chemist, right? I'm not even an organic chemist. I'm actually a biochemist, right? But there's a lot of organic chemistry in biochemistry as implied, and so the skills are transferable. Whereas, I mean, this guy, he was an absolute organic chemist. All he did all day long was organic chemistry, you know, and that's his thing, you know. But when he was an undergrad, he took organic chemistry, and on his first exam, he got a 55%. Obviously, his professor had a normal grading scale, okay? And he was like, yes, I got a 55%. And the reason why he was so excited about that is because the average in the class, and this was like a class of 400, I think he said, the average in the class was a 25%, right? Like, holy crap. You know, so he was like, yes, I beat the curve. You know, I beat the average. And so the reason why I tell you this story is because just because you don't do well in the very first exam doesn't mean that you've been condemned to being unsuccessful in organic chemistry, right? I really need you guys to buckle down and just, you know, work at it, work hard at it, right? And practice problems, right? And it's going to be hard. I'm telling you, it's going to be hard because it's a summer session. We're going fast. You're not going to have a lot of time, but that's how it's going to be. And so, unfortunately, that's what you signed up for. And we're very fortunate. You all are very fortunate to be in the class because up until the first day of class, I was having students beg me to let them in the class. And I have no power, you know, in allowing anyone in my class or dropping anyone in from my class. I mean, that is completely up to the registrar's office and the dean and all that. I have no power in waitlisting students or anything like that. And I had students every single day asking me, please let me in your class. I know it's full, but please let me in your class, you know. And I couldn't do anything about it. You know, the class was already at capacity. And, I mean, it was over capacity, actually. And so there was nothing I could do about it. So we are all fortunate that we were able to get in the class. And so I want you to be able to be successful in the class. And that one professor who got that 55, he was super excited about it because he was, you know, he beat the average by 25 points, you know. He is an organic professor today, right? Like one of the best, like well recognized, and in the scientific community. And so I just want you to know that he didn't keep on thinking about it that way, you know. He didn't keep on thinking about organic chemistry as being a class where I need to beat the average, because that is already going to put you on a path to not succeeding in organic chemistry. You need to do your best every single time and get the highest score possible every single time. You don't try to beat the average. You know, try to beat yourself, right? Try to challenge yourself and worry about yourself. Don't worry about the class average. Okay? All right. So that being said, I'm going to go ahead and get started on going through this exam. And a couple of things before I do that. There were a couple of incorrect grading, or some grading errors in the exam, and so because of that and some other mitigating factors, I've decided that I'm going to give everyone a 16-point curve. That is 1-6, right? A 16-point curve on your exam. So say you got an 84 on the exam, that means you got 100 on the exam, 100%. Okay. I'm not saying that's going to happen every single time, but sometimes there are grading errors, and they're beyond my control, and so and I don't want you to fail. I want you to succeed at this. All right. So make sure you are, watching my videos, practicing problems. Don't forget to sign up for Wiley Plus and watch those videos from David Klein. I mean, I'll tell you now, David Klein. I was telling guys in the very first semester that when I was in organic chemistry, as an undergrad, the book that I used was this McMurray book right here, right? And let me just tell you, it's not that great. And McMurray didn't go through with videos teaching me how to do it. When I finally got to grad school was when I learned about David Klein and got a copy of his book and saw his videos, and that's when it really clicked for me in grad school because of David Klein. So we are super fortunate that David Klein is here to teach us these days, right? So that being said, let's get started. I'll change over to the presentation view here, or actually I guess it's PDF view. And see, I even wrote my name at the top because I'm taking the exam like you guys are, okay? So, all right. So, first question. What is the difference between inorganic chemistry and organic chemistry? Or, sorry, not chemistry, compounds, right? This is an easy question because it was the very first sentence I said in class, right? When we started lecture, it is D, right? Organic compounds contain carbon, okay? Organic compounds contain carbon. Inorganic compounds contain other things like ionic compounds. I mean, ionic ions, like ionic ions. That sounds redundant. Cations, there we go. So let's take a look at number 2 now. It says, what is the correct Lewis structure for the molecule in the box, including the formal charges, if any? Well, the way I would first work this problem, right, just a regular formal charge and then Lewis structure problem, is I would identify how many valence electrons there are. So the hydrogen has 1 electron, the nitrogen has 5 electrons, right, and then the oxygen has 6 electrons, but that's times 3, right, because there's 3 oxygens. Okay, so all that together means that we have a total of 24 electrons, right? 24 valence electrons. Am I right about that? Am I doing my head math right? 6 times 3 is 18, plus 6 is 24. That's correct, right? So that's the first thing we do. I have to fill in 24 electrons, okay? The next thing is the most common question that's asked about Lewis dot structures is, how do I know where to start? Like, what is the central atom? Well, we know it can't be hydrogen because hydrogen is monovalent. And sometimes it could be oxygen, but oxygen is really just divalent, right? The one that has the possibility of the most stable bonds is nitrogen because it's trivalent, right? So in this case, nitrogen would definitely be the one in the center, okay? And now what I would do is I would fill in all the atoms all around nitrogen with just sigma bonds, okay? So oxygen, 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 all 3 right there with sigma bonds. Makes sense, right? But then you're asking yourself, where does the hydrogen go? Well, this is nitric acid, by the way, right? HNO3, right? And so you could put it on the nitrogen, right? But remember, at this point, you've already filled up the normal valency of nitrogen, it being trivalent, right? But you haven't filled up the normal valency of oxygens yet, right? They can still, each one of them can still accept another bond. So just for giggles, I'm going to put it on this side, right here, okay? And so that's the basic structure, Lewis dot structure of this nitric acid. Now we've got to fill in the electrons. So just like you've always been taught before, you got to fill up the octets, right? So hydrogen already has its octet because it's actually a ditet. It only has 2 electrons in the outer shell. But oxygen here requires 2 more electrons, right? And then each of these oxygens require 2 more electrons, right? And each of these oxygens require 2 more, oh, I keep on saying electrons, I'm sorry, 2 more electron pairs, okay? And so that's what oxygen normally looks like. So let's go ahead and count this up. How many electrons do we have so far? 2, 4, 6, 8, 10, 12, 14, 16, 20, sorry, 18, 20. Right, we still have 4 electrons left over. Well, don't forget that there's also a lone pair on nitrogen. That makes it 22. Now we have 2 electrons left over, right? Where do we put the last 2 electrons? Well, you could put it either on either oxygen, the one at the top or the one on the right side. Let's just go ahead and put it on the one on the right side. And when an oxygen has 3 pairs of electrons, 3 lone pairs of electrons, it's a negative charge. Right? And then, what do we do now? We have this oxygen left over here, right? And this oxygen doesn't have enough electrons. So what does it have to do? It's going to have to share electrons with nitrogen, okay? So that makes this a double bond then, right? And then the lone pair of electrons on nitrogen turns into a plus sign, right? Turns into a plus sign. That sort of looks like a plus sign. Let me just redraw that plus sign for you. Let's just do this, and this, and then this. There we go. A plus sign. Okay? So that's what the Lewis dot structure would be for nitric acid. So let's go through each one of these and see if any of these, are consistent with what we've drawn here. Okay? The first one, that's interesting, right? We're good with having the nitrogen in the center, right? But the problem here is that, look at this. There is 10 electrons surrounding oxygen, right? I mean, that's crazy. 3, right, lone pairs plus a double bond. Wow. Then, if you look down here, this nitrogen, the center nitrogen, also has 10 electrons, right? Wow. I mean, we violated all kinds of octet rules there, so that can't be that one. Let's take a look at this guy now. Another instance here where we have an oxygen with 10 electrons, right? So it can't be that guy. Definitely can't be that guy. Here we have an oxygen in the center, not the nitrogen in the center, right? And when it did that, it actually violated its valence because it's a divalent molecule. Remember, it's not tetravalent like a carbon, so it can't be that one, right? Oh, and this guy is our guy right here. See, same exact thing. 2 pairs of lone pairs on the hydroxyl or alcohol right there, right? And then 2 lone pairs on the carbonyl or not carbonyl. Sorry, it's connected to a nitrogen. Oxygen right there at the top, and then plus charge on the nitrogen, minus charge on the oxygen on the right, and there are 3 pairs of electrons there. 3 pair of lone pair electrons there. So it's definitely our guy, right? And then this guy, just for, again, giggles, wow. That would work, except that there's a total, like, charge, like, explosion happening right here. 3 negative charges around there, right? And then 1 plus charge gives you an overall negative charge of 2. Those formal charges are all over the place, so that's not a very stable molecule. That's not a very stable molecule. And that's why the hydrogen also shouldn't be attached to the nitrogen, right? Makes sense. Makes sense. And so the answer is D, structure 4. Which of the following is the correct depiction of a dipole moment for CF bond, or carbon-fluorine bond, right? So remember, when you're doing this, it's all about electronegativity. And fluorine is way more electronegative than carbon. And so the dipole would go like this, right? So what's the answer there? The answer there is 2, or B. Oh, see, this is what happens. You gotta be careful here, man. Careful. See, I'm like writing it so fast that I didn't look what I drew here. I drew the right answer right there, but look which one I circled. I circled the wrong one, right? You got to be careful about that stuff. The answer is actually A. Okay. So, I mean that kind of stuff happens to me on tests all the time, right? When I'm like, I have the right answer written down, but for some reason I circled the wrong one. Pay attention, Fong. Pay attention. Okay. This one's easy. Orbitals with the same energy are called what? They're called degenerate. That's B. Right? B. Okay. That's just a vocabulary word. You can look that up. Which type of bonding has circular symmetry with respect to the bond axis? Right? That would be the sigma bond, which makes sense because the sigma bond is what creates the the two s orbitals, right, that are like spherical, come together and make a sigma bond, and now it's just a big oval, so, or ellipse, right? So that's definitely kind of a self-explanatory thing, right? Maybe I should just draw it for you real quick since we're just having such a great time. Here we go. Here's the 1s orbital. Here's the 1s orbital. They come together. Right? They come together, and now you have an ellipse. Right? That's your sigma bond. Okay? So the next question. Which molecular orbitals are formed when the 1s orbital of 2 hydrogen atoms combine to form a hydrogen molecule? Right? Hydrogen molecule. Well, remember what I said what the rule was. When you have two atomic orbitals, and you bring them together to make a molecular orbital, you always get the same number of molecular orbitals as you have atomic orbitals, right? So the question is, what's the composition of these molecular orbitals, right? So since you already know that there has to be at least 2, or not at least 2, but there are 2, right? Then the ones that say only 1 are ruled out. Okay? That it can't be that answer, right? So then the question is then, is it 2 bonding molecular orbitals? Is it 2 anti-bonding molecular orbitals, or is it 1 of each? Right? Well, let's draw it out and look, right? Remember when I did this before, right? Where we have the 1s orbital, right? And we had an electron there. And we had a 1s orbital over here with an electron there, right? And then when those two come together, they make a bonding molecular orbital, right? At the bottom. That's where the electrons go. Bonding MO. Bonding MO. I promise that says MO, right? Molecular orbital. And if you recall, the bonding MO looks like this. Okay? So the other molecular orbital was up here, right? You recall what that one looked like? It was like this. Right? And it had a node down it. Is that a bonding molecular MO? No. That's an anti-bonding molecular MO. Anti-bonding molecular MO. Anti-bonding MO. Right? Not modus operandi, but molecular orbital. So the answer then is what? It's E. Okay. Let's keep on moving here. According to molecular orbital theory, the lowest energy molecular orbital that is unoccupied by electrons is referred to what? Well, that one's easy, right? Because it actually is in the name. LUMO stands for lowest unoccupied molecular orbital. So the answer is B there. And just for, giggles, LCAO actually stands for linear combination of atomic orbitals, right? And if you remember, that actually comes from the valence bond theory. So LaCow, or linear combinations of molecular orbitals, can't be the answer because we're talking about molecular orbital theory here, not valence bond theory. Degenerate is easy, right? That just means same energy. HOMO is highest occupied molecular orbital. And then antibonding is just a type of molecular orbital. So none of those would be right. It would be LUMO. Next, the interaction of the following two atomic orbitals results in what kind of molecular orbital? So these here, right, are out of phase with each other. Okay. So remember that when these are actually pi orbitals, by the way, right? They're not spherical, so they're not s orbitals, so they're pi orbitals. And pi orbitals come together to make what? Pi bonds. Okay. But to make a pi bond, you actually have to be in phase. Remember? Colored up here, and then not colored at the bottom, right? And then you can make a bond. But these are out of phase, right? So what is it going to be making if it doesn't make a bonding molecular orbital? It makes a pi antibonding molecular orbital, right? E. Cool stuff, cool stuff. All right. The next question. Here we go. Name the hybridization state of each of the indicated atoms in the following compound. Well, this is easy. Remember, when you do hybridization states, all you have to do is count up the number of electron domains, right? Either lone pairs or bonds, right? Like actual bonds. And that gives you the steric number, and the steric number gives you the hybridization state. Okay, so here on this oxygen right here, 1, 2, 3 electron domains, right? So that makes that an sp2. Carbon here has 1, 2. That makes carbon an sp hybridized. Nitrogen has 1, 2, 3. So he's sp2 hybridized, right? And then good old carbon number 4 over here, right, has 1, 2, 3, 4. So it's sp4 hybridized. So we're looking for sp2, sp3, sp2, sp, sp2, sp4. sp2, sp, s2, sp3. sp4? What the heck? There's no such thing as an sp4. Don't write that ever, okay? It's sp3. Yeah, don't write sp4. That doesn't exist, okay? There's no such thing as an sp4 hybridized carbon, okay? My bad. sp3 hybridized carbon. So the answer there is D. Okay. Next, rank the indicated in increasing order of bond length. Remember that the more bonds there are, the closer things get together, right? The closer the bonds are to, the electrons are to the nucleus and all that stuff. Remember in all our stabilization stuff that we were talking about before, right? So the strongest one, so increasing order of bond length, right? So the shortest one would be 2, right? Because that's the triple bond. And then the next one would be 1, because that's a double bond. And then the single bond would be the last, right? So it would be 2, 1, 3. Yes, 2, 1, 3. Next. Okay, so this is an interesting question, and the reason why it's interesting is because I actually got this wrong the first time I took the test. Whenever I write a test, I like to, actually take the test to make sure that it's doable. And the funny thing, I wrote the test and I got this wrong. And the reason why I got this wrong is because I read the question wrong. For some reason, I thought that said increasing, but it says decreasing. So I actually did it backwards and got the wrong answer. So make sure you read these questions very, very clearly, okay? Very, very clearly. Understand what the question's asking for. So rank the following compounds in order of decreasing dipole moment, right? So you want to go from the largest dipole, okay, the largest dipole, to the smallest dipole, okay? Some reason I did it the other way around when I took this test. My own test I took, and I got it wrong, right? You look at number 2 here, right? 2 is actually got a 0 dipole, right? Its dipole is 0. Why? Because you cut this thing in half, it looks symmetrical. It's a mirror image, right? It's the same both sides. So there's no dipole there, right? So you already know that 2 is going to be the last number, okay? 2 is going to be the last one. And then you're going to rank the next 2, right? So if we look at this one does have a slight dipole moment, right? But it's still pretty close to that center. That carbonyl is still pretty close to the center, right there over the at the very bottom. So it's got some dipole, but not strong. Not, you know, when it's almost as symmetrical as the other guy, right? Number 2. But if you look at this one, number 3, both carbonyls are on the same side. Right? Both carbonyls are on the same side, which means the dipole is going this way. Right? It's going that way. And this side is way more partially positive, right? And this side is way more partially negative, which means 3 would be the strongest. The strongest, the highest dipole moment, strongest dipole moment. So the answer there would be 3, 1, then 2. Cool stuff, cool stuff. All right. Identify the following compounds that have the greatest. See, this is tricky, right? Because it says compounds, right? It's like, is there one or is there more than one? Well, it says identify the following compound having the greatest London dispersion forces. And remember what I said about London dispersion forces. The bigger the molecule is, right, and the more flat it is, the more surface area it has, and the more of those two things make it the stronger London, the greatest London dispersion force. Well, that guy's branched right there, right? So it can't be him. Can't be him. That guy is also branched, so it can't be him, right? Now we're stuck with these 2 flat molecules. Which is the bigger one? It's this one, right? This one has 6 carbons, hexane. This one has 5 carbons, pentane. So the answer is D. Okay? Answer is D. Let's keep on trucking. Identify the following compound expected to be most soluble in butane. Remember what I said about that, about solubility. Like likes like, or like seeks like, or whatever you want to call it. Or like dissolves like, right? I like the word, I like the phrase like likes. So it's like L squared. No, cubed. L cubed. Right? L cubed. Likes. Likes. Right? So the only molecule here that is as hydrocarbonic as that one, butane, right, is going to be pentane. They almost like they look almost exactly alike, except for pentane has 1 extra carbon. So obviously these two are going to like each other, and they'll be soluble, right? This is 2 polar, got a chlorine on it. This has an oxygen on it. This is also 2 polar, right? So it's going to be A. Next time we go. No, I'm sorry. Next question. Didn't mean to draw there. I was trying to pull it down and it wasn't working. There we go. The following structure for propranolol, propranolol. That's a really hard drug name. An antihypertensive drug. I guess it prevents or helps treat hypertension, in your cardiovascular system. Identify the hybridization state of the molecular geometry. The hybridization hybridization state, molecular geometry, and approximate bond angle of the nitrogen in there. Well, let's take a look at that guy right there. We know that he's got a lone pair at the top, right? He's sp3 because he has 1, 2, 3, 4 electron domains, right? So if you're sp3, I almost said sp4 again. If you're sp3, right, and you have a lone pair at the top, right? Right? What are you going to be? You're going to be trigonal bipyramidal, correct? And trigonal bipyramidal has bond angles of 109.5. Good stuff. Good stuff. Okay. I'm trying to make the. It's hard to like use your Apple Pencil to like make these things straight. It's like might as well just have a mouse. But you know, my mouse can't draw as well. Okay, so draw the correct line angle structure, or sorry, bond line structure for CH3, CC, CH2, 3, C, CH3, blah, 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 blah. This is one of those things you're going to take one at a time, okay? First thing you notice here is that it's got a methyl group, CH3, right? Can't be this first one because there's no methyl group right there, right? Also can't be this first one because even though it has a methyl group there, there's an oxygen right connected to the methyl group, and that's not happening on this side, right? So can't be that one. Next thing to notice here is that you have a triple bond right after the methyl group. So all of these have triple bonds after the methyl group. Okay, so that's a check for all of them right there. Check on the methyl group. And then next thing you get is 3 CH2s in a row. Okay, that's only 2 CH2s in a row. That's only 2 CH2s in a row. That's only 1 CH2 in a row. Ah, here we go. 1, 2, 3. So you don't even have to go through the whole thing. Forget the rest of that crap. Almost cursed. Sorry. Forget the rest of that crap. None of these have 3 CH2s in a row. So which one is it? It's going to be that one. Structure 4. Good times. Good times, right? Good times. Who would have thought an exam would be so fun to talk about, right? So fun. Next one. Norethylnodrel. Come up with these drug names. A component of the first combined oral contraceptive. Interesting. Has the following structure. Identify the functional groups on each. Oh, that's fun stuff. We've got a carbonyl here, which is more specifically a ketone, because it's got R groups on both sides. We've got an alkene here. We've got a hydroxyl or an alcohol here, and then we have an alkyne there. So ketone, alkene, alcohol, alkyne. Ketone, alkene, alcohol, alkyne. There it is, E. So that's one of those things where you just got to memorize what the functional groups are. Okay, got to memorize those functional groups. Okay, next. Okay. God, see, my Apple Pencil's just acting up. Here we go. Identify the structure that shows the correct placement of lone pairs on the compound illustrated below. All right. Well, this is pretty easy. We already know that nitrogen is trigonal bipyramidal. No, sorry, trigonal pyramidal. Yes, trigonal pyramidal when it's got 3 bonds to it because there's a lone pair at the top. Okay, so you can already rule out that one there because it doesn't have any lone pairs. Okay, doesn't have any lone pairs. We know that oxygen has 2 lone pairs when it's neutral and fully octeted, right? That's good. So we can cross that one out because that one only has 1 lone pair. Okay, so that just leaves these 3. When oxygen shares 3 bonds, or not shares 3 bonds, but has a double bond and a single bond on it, right? It always has a positive charge, and the reason why is because it's lost one of its lone pairs to that sharing, which means it's got 1 lone pair left over, right? So which one is that one? Oh, I just noticed that you can actually cross this one out too, because that one has 2 lone pairs on nitrogen. That's like 10 electrons. That's not right. So really it's between 2 and 5. You can't even see what 5 is, but 5 is wrong. So the answer is 2. B. Right? B. And the reason why 5 is wrong too is I guess I can move my head out the way so you can see it real quick. It has 2 lone pairs on this positive oxygen here. That's like 10 electrons. You can't do that, right? That's just not possible. Okay, I'm going to come back now. There we go. Next one is numeral 18. Oh man, we're getting towards the end here. We're getting towards the end of the exam. This is good stuff. Which of the following pairs are resonance structures of each other? Well, this is one of those things where you gotta know the patterns, right? The resonance pair, the resonance patterns that you can recognize, right? So these are both just alkanes, no double bonds, no pi bonds, no carbocations, no lone pairs, no carb anions, nothing. So this is definitely not a resonance structure at all, much less a resonance structure of each other. Now this one, it does have a pi bond there, but remember the rules or the recognition says, like, you know, an alkenic lone pair, or a not alkenic, what do they call it? Allylic lone pair, or a carbocation adjacent to a lone pair, or a carbocation adjacent to a double bond, and so all these things that require lone pairs, or a charged species, a carbocation or carbanion, and that's not present in number 3 at all. Okay, well, it doesn't recognize any of those, so that's not one. Okay, that's not one at all. Now this one here, right? You definitely have a resonance structure going on here, right? But is it correct? We have I forgot which pattern is this one? Which is the one where you have 2 electronegative? That's pattern 4. So pattern 4 here, right, where you have oxygen and carbon, 2 different electronegativity atoms connected to each other, right? And to boot, there's a lone pair next door to a double bond, right? So you definitely could do a resonance structure where this came down like that, right, to form a double bond, the carbonyl. But then this double bond has to break and then leave the carbon at the end of the I guess it's an acetone, right, with a carbanion. The problem is, though, that the structure over here doesn't have a carbanion there. It needs to have a negative charge right here for it to be correct. So that's not right either. So which one is the correct one? By process of elimination, it's 4, right? But it kind of makes sense, though, because you have now a lone pair next to a carbanion, right? And that's how you make... I just drew that backwards. I apologize. Let me do that again. Undo. I should have drawn it on this one first. You have a double bond here, or you have a bond here, right? And it can go like this, right? It can go like that. Or it can go the other way too, right? And go back and forth between that carbon and the nitrogen, right? Because it's a 2, again, that's a pattern 4 recognition of resonance, which is 2 different electronegative atoms connected to each other. I said I drew it backwards a second ago, but I didn't. See? So, number 19, right? Which of the following example violates the rule for curved arrows? Well, if you take a look at this, you don't even really need to know any of the pattern recognition things, right, for resonance, because you see here, if on number 1, on structure number 1, if this arrow happened, moving this double bond to connect with the nitrogen, that would leave nitrogen with 10 bonds. That's 10 electrons. I mean, that's just not possible. You can't do that. Remember, 10 electrons is violating the octet rule. So it can't be that. So you already know that number 1 violates the rules for curved arrows, right? Let's look at the rest of them. Well, you definitely can do this. We have an allylic carbocation right here. So that can definitely move up that way. Okay. And then in the next resonance structure, you would just have a carbocation there now, right? Plus sign there with the double bond to the carbon up there. And then for this one, this is actually the same thing as the previous one right here. See? Right there. Same thing. Except that it has a benzene ring attached to it, so... But that's the same thing, so we know that's possible. Now, let's take a look at this one right here, right? Now here we have an allylic lone pair, which actually does obey, or does look like a pattern 1, which is a allylic lone pair of resonance, right? The problem, though, is that with this one, they drew one arrow, signifying that a double bond will form between the oxygen and the carbon, which is fine. But then, you need to draw another arrow showing that this double bond moves towards that carbon there, leaving you with a carb anion. And since it doesn't have that arrow there, it's also a violation. So the answer here would be B, 1 and 3. Okay. Next. Oh man, we're starting to get into all the resonance questions, right? Oops, went too far. Come on now, you can do this. Here we go. Okay, number 20. Identify the resonance structure indicated by the curved arrows, right? So this is pretty simple. Again, we have an allylic lone pair here. I'm going to abbreviate that by saying ALP for allylic lone pair. So that's pattern 1 of the resonance recognition rules, right? So that's definitely a doable resonance structure. And so if the electrons from this lone pair come down and form a double bond here, that means you'll have a double bond between nitrogen and that carbon there. Okay. And that means that you have a plus charge on the nitrogen. Okay. But when you do that, this double bond moves here. Right? And then when you do that, this double bond moves so that there's now a carb anion on this guy right here. And don't forget that there's a double bond up there too, right? That doesn't participate. Okay, so what structure matches that guy? It's going to be C. Let's take a look at the next one now. Number 21. Here we can see that the move it up and down. There we go. Here, identify the options given the proper curved arrows to convert the first identify the options given the proper curved arrow to convert the first resonance structure into the second resonance structure. So basically, just draw the arrows. Which one is? How do you draw the arrows so that it gives you the correct resonance structure? Well, first let's identify what kind of resonance pattern this is. Right? We have a lone pair right there. Okay. Adjacent to a carbocation right there. So we'll abbreviate that as LP adjacent to a carbocation, right? That's actually pattern 3, right? That's pattern 3. And when you have pattern 3, what happens? Well, the lone pair comes down and forms a double bond between the oxygen and the carbocation, and that's why you get this, right? No charge left over because now you have a triple bond to the oxygen and the plus charge is over there. So which one of these is it? Well, it definitely isn't this one. It's only one-step reaction, or one-step thing, so it's not two arrows, right? Here, that shows something moving towards the oxygen. Well, what? How is that even possible when that's a carbocation? It's missing an electron, right? What's moving? So it can't be that one. Okay. Then here it shows this bond breaking from the carbocation to go to the oxygen, so it's definitely not that one. So now you're left with this one and this one. Okay. Now a lot of people get confused, right? But the arrows where they point is very important, right? When you're drawing this arrow from the lone pair of the oxygen to that bond, it has to point to the bond, right? It's not pointing towards the carbocation. That's bad. You don't want that, right? Because you're forming a double bond, as seen in this structure right here, right? So when you draw an arrow from the lone pair, from the oxygen to the carbocation, right? That looks like it's transferring electrons from that oxygen straight to the carbocation, not even forming a double bond, but you're forming a double bond, as seen there, right? So that's why that's incorrect. It has to show the arrow going pointed straight to, right? Straight to the bond. Okay? Straight to the bond. Next. Oops. Keep on missing the damn scroll bar there. Excuse me. Didn't mean to curse. There we go. Okay. Identify the options given the proper curved arrows to convert the first resonance structure to the second resonance structure. So same thing again as the last question, right? Which arrows are correct? How do you make the second structure from the first structure? Okay. Well, first of all, we can see that this is two electronegative, right, atoms, different, connected to each other. So that's a pattern 4 recognition there. Okay. And so how do we start this thing? How do we get to where we're going here? Okay. Well, the first thing that has to happen here is the lone pair from the oxygen comes down and forms a double bond. So that's this double bond right here in the structure. Okay. And then once that happens, that breaks this lone pair so that the electrons from the lone pair go up to the oxygen now. And that's what makes this negative charge right here. So that's what the arrow should look like, right? It can't be this one because it shows two arrows going away from each other. And remember, electrons flow in a single direction. They don't just go, split, pairs. Electron pairs flow in a direction, right? Sometimes you'll see like radicals where are single electrons, right? And they'll split, but we haven't got that far yet, okay? So this is definitely not this guy, right? Definitely not this guy. This one has two electrons coming toward each other. Wrong. Two pairs of electrons coming toward each other. Wrong, right? And the problem with what's happening here, right, is that when you pull these electrons to come down here like this, it's almost like you're putting a triple bond there between the oxygen and the carbon, right? And that breaks this bond, right, from the carbon because the carbon only has 4 bonds. So that's not right either. So the answer is definitely 2. Okay? Or answer B. Answer B. Okay? Next one. Oh, God, I keep on drawing on the thing. There we go. For the structures shown in the box below, identify the corresponding correct resonance structures. Okay. Cool, cool. So we have this guy here, right? And a couple things can happen, right? A couple things can happen. We can have this lone pair come this way, right? And do this. Okay? So that's one structure right there. I promise that's a 6-membered ring right there. It doesn't look like it, but there we go. So which one looks like that? This one, number 3. So that's one of them. Okay. The other thing that could happen is that this lone pair can come this way. Okay. So that gives you this structure. Where that stays the same, and then in the 6-membered, almost drew a nitrogen, a sulfur there. That's weird. Undo. Let me draw that again. Alright. And then there's going to be a double bond there from that arrow. And then the double bond that used to be between the carbon and the nitrogen adds a lone pair up here. So now we have a minus charge. Right? So which one looks like that? It's going to be 4. So, can't be that one. Can't be that one. The answer then is 3 and 4. C. Cool. And then the last page here, more resonance structures, right? Identify the significance. Oh, I forgot to tell you what the the recognition pattern here, right? What's the recognition pattern on this resonance structure? It is actually, again, we have here a lone pair, so that's LPA for allylic lone pair. LPA? No. ALP, right? So that's an allylic lone pair. Right? Allylic lone pair. And that's actually pattern 1. Okay? It actually helps a lot if you identify the pattern of resonance before you actually do the resonance structure, right? Or draw the arrows. Okay, on the next one, we have identify the most significant resonance structure, right? So which one is going to be the most stable of them all? You know, the one that is the highest contributor of resonance here, okay? Well, let's, just for giggles, let's recognize the, or not recognize, but let's identify the resonance pattern, right? So here we have 2 electronegative atoms difference. Okay, 2 electron atom difference. So that's what that is. Okay. With the pi bond. Let's forget that part. With the pi bond. Okay. So all these resonance structures actually are correct, right? They are correct because this arrow can come down here, right, leaving you with the carbocation there, and then this arrow here can come down, not this arrow, this bond can come down there, right, leaving you with this double bond that you see here and this carbocation there, and then this double bond can come down here like this, leaving you with that double bond there and this carbocation there. So they're all valid resonance structures. So which one is the most stable, or the one that is going to be contributing the most to these structures? Well, one of the most important rules of significant resonance structures is having a full octet. Okay. Well, when you have a carbocation, that's not a full octet. This has a full octet. I mean, this one doesn't have a full octet either because that's a carbocation. There's another carbocation with not a full octet. So it's none of those, right? Because they all have carbocations with no full octets. But we do have an oxygen there, and it actually does have a full octet, right? Because it's got 3 bonds to it and a lone pair still. And it's still positively charged, but that's okay because it's got a full octet. So the most stable one is structure 1, A. And then the last one is about hybrid structures, right? So this is another allylic lone pair, ALP. So that's pattern 1 again, right? for resonance. Let's see which one is the resonance hybrid, right? And the easiest way to do this is to actually just draw out the resonance structures. So if I were to take this lone pair like that, okay, to form a bond there, then this bond here becomes a carb anion on that carbon in the center. So let's draw it out. Right? And then I have negative charge there and a double bond here. Okay? Then if I draw another arrow and push that electron, that lone pair there to form a bond there, right? Then the oxygen will receive the lone pair the lone pair from that bond, that double bond. So it looks like this. Okay. With a negative charge, because it has 3 lone pairs now, right? So we have a negative charge there, we have a negative charge there, and we have a negative charge there. Which one actually represents that? Well, it's definitely not this one, V, because V has 3 positive charges, right? 3 positive charges. And it can't be this one here because we never had 1 positive charge and 1 negative charge, so it can't be 3. Right? Same with this here, never had a carbocation there, can't be that one there. So now it's between this one and this one. Which one do you think it is? Well, remember that we actually started with a negative charge right over here at the very first carbon. This one puts a partial positive on that carbon there, right? And not once was there ever a charge on that carbon or on this carbon. So it can't be that one. The answer here is A. Okay? And that actually ends the exam. I hope this was helpful for you. Make sure you go through and watch this video, draw these things out. I was going to post what I drew here on the on Blackboard for you so that you can actually look at it and stuff and print it out and study it with my handwriting on it. But that's not going to help you. You need to actually draw this stuff out yourself. Okay? You need to draw. You need to draw this stuff out yourself. So get yourself a white piece of paper and just write out the problem, because drawing the structures is good practice, right? And then write out the stuff that you need to write to get to the answer, and then there you go, right? That's how you practice this stuff. Okay? All right. I'll see you in the next video for the review of Quiz 1, and a second video, or a third video rather, for a review of Quiz 2. Okay?